This is an addendum to the previous video about variance and standard deviation. I didn't say words about why standard deviation is the square root of variance. I didn't talk that through in a clear way at all. So I'm going to say a few words here to try to make sense of that. Okay, so I talked a lot about the definition of variance and two ways you can write it. The definition goes like this. So it's the squared distance from your mean. Mean squared distance from your mean. Okay, that's the definition. And we saw another way that you can write it to do calculations. But this shape is the argument for why standard deviation is the square root of that mess. And it's a little bit of a cheat. And what I mean by that is we know we spend a lot of time at GCSE and sometimes at A-level yelling very, very, very loudly that, oops, that's not what I wanted. That, well, okay, no, it's true. We yell very loudly that that's not true. And we also yell very loudly that that's not true either. That when you're doing a sum of squares, that the square root of that quantity is not just the square root of each piece individually. We yell a lot about this and threaten to send the maths police after you at 3 in the morning if you do, and all stuff and things. And we know that it's not true, because if you say something like 3 squared plus 4 squared, everybody's favorite Pythagorean numbers, 3 squared plus 4 squared, that's going to give you the square root of 25, which is 5, but I know that that's not the same thing as 3 plus 4, which is 7. Not the same. Yell, yell, yell. Okay, and what do we do in stats world? We say, oh, well, okay, if you're going to go adding up all these squares, you know, the difference from your first data point and the mean, second data point and the mean, blah, 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 your last data point and your mean, and you add up all the squares, and you take that average, and that's your variance. But you've added up a bunch of squares, so you square root it to undo the squaring. And you're like, but it doesn't work like that. You're not going to come back to exactly the right number, and that's true. You're not going to come back to, if you took the actual distances, you know, the modulus of the distances and add them up, it's not going to be the same. And for the same reason that that is not the same thing as that. But it's good enough. It's close enough. We are not claiming that this square rooting undoes the squaring. We're saying it's good enough. That this is nicer for algebraic reasons, and it turns out really nice in probability world to take an analogy of this definition in probability distribution world. We know that it's not exactly the average distance from the mean, but it's ish enough, right? 5, 7, they're ishy, they're near each other. It's good enough. And that's the justification for standard deviation being the square root of the variance. That if the variance is the average squared distance from the mean, then if you square root that, if you square root the average squared distance, you should get the average distance from the mean. If you square root a squared distance, you get a distance. It's ishy, but it's good enough. And I will refrain from more comments about what stats does to maths. Gosh, that's really unfair. Statistics is firmly based on proper solid mathematics, and I promise you that, even when it seems hand wavy. These are useful definitions, and they're good enough for what we need, and that's what we roll with. Okay, thank you. That's what I wanted to say.